Assalamualaikum, students and friends. Today's lecture is focused on a multiple choice question involving an object in a non-uniform circular motion. How do we describe and analyze the velocity and acceleration of this body, as well as the net force acting on it? You will know the answers by sticking around till the end of this video. Watch and learn. The question is, a ball tied to one end of a string is whirled in a counterclockwise direction along a vertical circular path. Consider the positions of the ball at points A, B, C, and D as shown in this figure. We also emphasize that the geographic direction in this diagram is such that the north-south axis is parallel to the axis of the circular plane at the center, as indicated by the cross symbol. The north direction is directed into the screen, and the dot symbol means that the south direction is into the reader. Which of the following statements is or are correct? One or more answers. Option letter A, it has the greatest speed at point C and the least speed at point A. Option letter B, its total acceleration at any given point in the circle is directed to the center of the circle. Option letter C, its total acceleration is due to the pull of gravity and the tension in the string. And option letter D, the F net at point C is upward and downward at point A. Since the ball is whirled in a counterclockwise direction around a vertical circular path such that the circular plane is perpendicular to the surface, or that the axis of rotation is parallel to the ground surface, we can describe its instantaneous velocity to be the tangent to the point in the circle. Hence, it is denoted by V sub tan. V sub tan, or the tangential velocity, is minimum at point A, where it's considered the topmost point in the path, and its maximum at point C, the lowest point in the path. From the topmost point, or point A, through the lowest point, point C, the magnitude of the tangential velocity is, in fact, increasing. All right? And on its way up through the circle, the tangential velocity is decreasing in magnitude. That's from point C to point A. And the magnitude of this tangential velocity v sub tan at any instant is just equal to 2 pi r divided by capital T, where r is the radius of the circle and capital T is the period or the time for one complete revolution. And we can also express this instantaneous tangential velocity in terms of the angular velocity omega. That is, v sub tan, or the tangential velocity, is also equal to omega times the radius r. Because the tangential velocity is always changing its direction, there arises a centripetal acceleration a sub c, alright, whose direction, as the term suggests, is always towards the center of the circle. However, relative to the ground surface, the direction of a sub c, in fact, varies. Alright? For example, at point A, it is directed downward perpendicular to the ground surface. At point C, it is directed upward away from the ground surface. At point B, its direction is eastward, and at point D, it is directed westward. The centripetal acceleration, alright, a sub c, arises due to the continuously changing direction of the tangential velocity, and mathematically, we can define the magnitude of this instantaneous acceleration to be the limit of delta v over delta t as delta t approaches 0. And if you're going to do your derivatives, this instantaneous acceleration will be equal to the square of the tangential velocity v squared divided by the radius r. Alright? And it is also related to the angular speed omega as shown in this equation. That is, a sub c is also equal to the product of the square of the angular velocity omega and the radius of the circle small letter r. Because the magnitude of the tangential velocity is changing, that is, it is increasing as the ball passes point A and continues through points B and C. The ball has a tangential acceleration a sub t. A sub t, alright, is positive as the ball moves from point A to point B and to point C. It is negative as the ball moves up from point C through points D to A. Alright? Notice there is no tangential acceleration at point A or at point C. This is because the direction of the force of gravity at these points A or C is perpendicular, all right, to the tangential velocity at these points. So, the force of gravity does not cause a change in the magnitude of the tangential velocity. All right? So, it is the effect of the force of gravity why the tangential velocity increases from point A, all right, to point B and to point C. And it's also the effect of force of gravity trying to pull the object or the ball downward so that as it passes point C on its way up, passing through point D, all right, on its way up to point A, we say that the tangential velocity is decreasing in magnitude. Hence, all right, the tangential acceleration is negative. Okay, positive on its way down and negative on its way up. All right, and the magnitude of this tangential acceleration, all right, is just equal to the change in the magnitude of the tangential velocity divided by the change in time. All right. So just like in the case of centripetal acceleration, all right, we can also get the limit of delta V, all right, over delta T as delta T approaches zero. And the magnitude of the tangential acceleration, all right, at such points like point B and point D or any other point except point A and point C, all right, the magnitude of the tangential acceleration can also be expressed in terms of the angular acceleration denoted by the Greek letter alpha multiplied by the radius of the circle. Right? So, the fact that the tangential acceleration, okay, is equal to alpha multiplied by the radius r, this suggests that the ball uh, has a changing angular velocity omega. All right. Considering the entire circular motion of the ball, we say that the angular velocity omega is not constant. All right. So, if the angular velocity omega is not constant, it follows that the body has what we call an angular acceleration denoted here by the Greek letter alpha. All right. So, uh, at any point in the circle, all right, other than points A and point C, we say that the actual linear acceleration of the body, all right, for example, at point B, because of the combination of the two linear acceleration a sub c and tangential acceleration a sub t, all right, there is that actual acceleration, all right, which is determined using the Pythagorean formula. All right? So we just get the square root of the square of a sub c plus the square of a sub t. All right? And to describe the direction of this actual acceleration, we can just calculate for the angle theta that the actual acceleration forms with the east direction using the formula arctangent of the ratio a sub t over a sub c. All right, so that's true for point B. When the ball is at point B, you will notice that the centripetal acceleration and the tangential acceleration are perpendicular. And so therefore, if you add them vectorially, all right, we will get the vector sum represented here by this diagonal arrow labeled as acceleration A, whose magnitude, as mentioned earlier, can be determined using the Pythagorean formula. All right, and that's also true for any other point like point D. At point D, again, we represent the actual acceleration by this arrow, all right, labeled here as A, which is, or which can be determined also using the Pythagorean formula, all right? So that's true for any other point except point A and point C, where we said that at point A and at point C, the acceleration of the body is just represented by the centripetal acceleration, a sub c, because at each point A or C, there is no tangential acceleration. Lastly, we also want to describe the forces acting on the ball, specifically at points A and C. All right? So at point A, the net force, take note that point A is the topmost point, all right, of the circular path. So at that point, um, the tension force exerted by the string, we label it as T sub 1, plus the downward pull of gravity constitute the net force, all right, because they are both directed downwards relative to the ground, all right? And if you're going to equate this net force, all right, to the formula for what we call centripetal force, mv squared divided by r, all right? So the net force T sub 1 plus mg, which is the weight of the ball, is equal to mv squared over r, where the speed here is considered the minimum speed, all right, of the ball. And if you're going to isolate the tension force T sub 1, we will get this working equation if you want to determine the magnitude of the tension T sub 1. All right? So it's just equal to the mass of the body of the ball multiplied by the square of the minimum speed divided by r minus, all right, acceleration due to gravity. So that actually means mv squared over r minus mg. We just factored out the mass m. So that is uh, when the ball is at its topmost point or point A. How about if the ball is at its lowest point or point C? Okay. How do you describe the net force? Right. So at point C, the net force would now become T sub 2, all right? That is the force of the tension of the string minus the weight of the ball mg. All right? Why the minus sign? It is because the tension force T sub 2 is now opposite to the direction of the weight or force of gravity on the ball. All right? So again, if you're going to equate this net force to the centripetal force formula and isolate T sub 2, this is what you will get. The mass of the ball multiplied by quantity V max squared divided by the radius r plus g, all right, which actually the t sub 2 here is equal to the sum of mv squared over r plus mg. We just factored out the mass m, and as you can see, all right, if you want to compare the two tensions, T sub 1 and T sub 2, which do you think has the greater magnitude? T sub 1 or T sub 2? Right. The answer is, of course, T sub 2 is greater than T sub 1. Why? Well, because for T sub 2, all right, we are multiplying the mass of the ball by the maximum tangential speed, V max. All right? Whereas in the case of T sub 1, all right, uh, we are multiplying the mass by the minimum tangential speed. And the other reason is the fact that for T sub 2, all right, we are also considering the effect of adding the weight of the ball. Whereas in the equation for T sub 1, we are subtracting the weight of the ball. So that is how we are able to say that T sub 2 in fact is greater than T sub 1. And in this situation, T sub 2 intuitively must be greater than T sub 1, because for the ball to be able to move up through the circular path, all right, while it's being pulled by gravity, all right, the tendency for the tension in the string, all right, is to have a greater value, okay, as compared to the force tension when the object, the ball, is at the topmost point. All right. So, what do you think will happen if the ball is at point A and then all of a sudden the force of the tension disappears? All right. So that happens if, while whirling the ball that is tied to the end of the string, just before it reaches point A, the string gets loose, or the string slackens. So it is like saying that the tension T1 becomes 0, right? What will happen to the ball? All right. So we base it from our formula for T sub 1. All right. So in this formula, if T sub 1 is equal to 0, then we say that the weight mg will just be equal to mb squared over r. All right. And canceling the mass m, all right, we will be able to come up with a formula for finding the value or the magnitude of the minimum speed or tangential speed. That is, the magnitude of the tangential speed, we call it v minimum, will just be equal to the square root, the product of the radius r and acceleration due to gravity. All right. This is the result of deriving the formula for finding T sub 1, all right, this equation over here, and we let the tension T sub 1 be equal to 0. So that makes mb minimum squared over r, okay, be equal to mg. All right. Then isolating for b minimum, this is what we get. What does this mean? All right. Uh, this v minimum is also called the critical speed of the body. Critical in the sense that if the speed or tangential speed of the body is less than or lower than this critical value, the object will not be able to make a perfect circular path. It will not be able to move in a perfect circular path, because in the first place, there will be no more centripetal force, right? Which in this situation was provided by the tension or by the string. So removing the string, all right, from the picture, all right, will also remove the so-called centripetal force that will be exerted on the ball, or that will give it what we call the centripetal acceleration. In short, if the net force is just the force of gravity, all right, and there is no centripetal force that will cause the body to accelerate towards the center of the circle, then how will it be able to make a perfect circular motion? All right. So this derived formula for the critical speed or velocity is important, especially when we are describing the motion of objects like the satellite, artificial satellites, all right, that are orbiting the Earth. If the tangential velocity of an artificial satellite happens to be less than the critical tangential velocity, then it will not be able to make a perfect circular path around the Earth, and the possibility for that artificial satellite to fall back to the Earth, okay, is very likely. Right? So, we will now go back to our multiple choice question. And so, in the question, which of the following statements is or are correct? Okay, we need one or more answers. For option letter A, it has the greatest speed at point C and least speed at point A. All right? Recall that point C is the lowest point of the ball in the circular path, all right? While point A is the topmost point in the circular path. And based on what we have discussed, this statement is considered correct. For option letter B, its total acceleration at any given point in the circle is directed to the center of the circle. All right? So, this is referring to the total acceleration, all right? Meaning the combined acceleration that is centripetal as well as tangential, all right? Uh, we said that if the tangential velocity of the body, all right, is either increasing or decreasing, there arises what we call a tangential acceleration. The tangential acceleration, all right, when added vectorially to the centripetal acceleration, simply using the Pythagorean theorem or formula, okay, and then getting the angle that the total acceleration forms with the horizontal, you will find out that, as we have discussed also, that the direction of this total acceleration is not always directed to the center of the circle, all right? Because it depends on the angle theta that is formed, all right, by the by this acceleration with the horizontal line. Except at point A and at point C, where there is no tangential acceleration, then the total acceleration is directed towards the center. In short, option letter B is not correct. Now, for option letter C, the total acceleration is due to the pull of gravity and the tension in the string. All right? Um, we relate this total acceleration, of course, to the total force acting on the body. In short, whatever is the net force, then such net force will also cause the body to have a total acceleration. And we said earlier that the net force, all right, is just the vector sum of the pull of gravity, mg, and the tension of the string. So, this statement, or option letter C, is also correct. And the last option, the net force at point C is directed upward and directed downward at point A. All right. So, we already said that the net force is always directed towards the center. All right. The net force is the centripetal force, okay, which by definition is always directed towards the center. And at the highest or topmost point around the circle, that is point A, both the tension and the pull of gravity is directed downwards towards the center. All right. While at the lowest point or point C, all right, the force of gravity is opposite to the direction of the force of the string or the tension force. All right. But the F net is simply the difference between the tension force and the force of gravity. Since the tension force, we label it in our diagram earlier as T sub 2, is greater than the pull of gravity, then therefore it follows that the tension force at point C is directed upward towards the center. So that means option C is also a correct statement. All right? So I think we're done with this video tutorial. Till the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.